I am going to write a little bit on this board. So the objects I'm going to be interested in are elliptic curves over Q. So we have an elliptic curve. And of course, the thing that we most want to know about such curves is a description of the set of Q rational points on the curve. It's a finitely generated abelian group, has such a structure. So if you can't describe all the points, perhaps you can at least say something about the rank of this group. And this is famously connected to the L function of the elliptic curve, or at least its order of vanishing at s equals 1 by the Burt-Swinnerton-Dyer conjecture. So that's the Burt-Swinnerton-Dyer conjecture. And so what I'm going to talk about today has a lot to do with sort of this conjecture and those objects. So let me first remind you of some of these theorems of Gross-Zaqier and Kolyvagin that are mentioned in the title. So suppose, for example, that the central value of the L function of the elliptic curve doesn't vanish. This is not 0. Then one of the things that was proved through the work of Gross-Zaqier and Kolyvagin was that, in fact, the set of rational points is finite. And the Tate-Shafarevich group of the curve is also finite. So these are both finite groups. This is, as I said, due primarily to the work of Gross-Zaqier and Kolyvagin through Kolyvagin's theory of Euler systems, in particular the Euler system for Heegner points. The reverse implication here, certainly in this strong sense and actually weaker, is also known. First, in the case of CM curves through the work of Greenberg, and then for more general curves through work of myself and Eric Ribam. There was some technical hypotheses on the conductor of the curve. It couldn't be square full, and that was removed by Shenwan in his PhD thesis. So if an elliptic curve over Q has as finite or Delvey group and the Tate-Shafarevich group is finite, then in fact the L function doesn't vanish. You can sort of weaken this hypothesis a little bit, but we'll leave it like that for cleanness. I don't really want to talk about that. What I would like to talk about, I can still put it on this one, is the situation when the derivative of the L function doesn't vanish. So in this case, the Burt-Swinnerton-Dyer conjecture is predicting that we ought to have rank 1, and this is in fact also known. So now the rank of the elliptic cube. Well, actually, the parity of the order, well, vanishes. I'm not making any assumptions, I guess, on the. Oh, okay. Equals 0 if you like. Okay. Now my board is spoiled. Equals 0. Right, I have to assume something about the sign of the function equation. So the rank of, actually that's not true. If it vanished, if it had sign of the functional equation was +1, then it vanishes to to even order, so then this wouldn't have been 0. But anyway, to satisfy all you guys, I'll say that. And again, Shavi is finite. Sorry, the rank is equal to 1. And so one might ask then also, what about this reverse implication? And so that's what I want to talk about initially. So let me say it this way. We can recast this a little bit more p-adically, so there's going to be an arrow that goes like this. I'm going to say then for each prime p, what I know from these two conditions is that the p-infinity Selmer group of the elliptic curve has co-rank 1. And I'll say a little bit in a minute what that is. And I know that if I take this and I look at it at the restriction map at the prime p, then it's landing in the cycles that come locally from the elliptic curve and the points over qp. And that's in fact a surjection. That being a surjection is a consequence of actually having the rank, and the co-rank 1 is then the consequence of the finiteness of the Shah. So let me remind you maybe what I mean by the Selmer group p-infinity v. This is just the set of classes, say in H1Q, with p-infinity torsion, such that under restriction, at all places x, this is actually vanishes in H1QV, not just not in the p-infinity torsion as a Galois module over the Galois group of QV, but actually when we pass through the entire set of points on the curve. And so equivalently, we could write that as saying that the restriction at v of x belongs to E of QV. I guess since I'm gone up to p-infinity torsion, tensor to QP, ZP. And that's for all v, places v. So this is some co-finitely generated ZP module. So if I take its Pontryagin dual, it's a finitely generated ZP module, and the rank of that dual is what I mean by the co-rank. So this would look like QP mod ZP plus some to some power plus something finite, and this is conjecturally this power here is the rank of the elliptic curve. And so what the first theorem I'm going to state is a statement that sort of says if we know these two facts here, then we actually can conclude this. So it's going to be expect this to imply that. In fact, you should expect if you know this for a single prime, that should imply that. And I'm going to sort of state a theorem that says if you know this for a single prime with some additional hypotheses on P and E, then in fact you do know this. So here's the first theorem. Let's call it theorem A. So let E over Q be an elliptic curve. Curve from P a prime. If the following conditions hold this way. First of all, I'm going to make a simplifying assumption that the conductor of E is square free. So let's give that conductor a name. It's square free. And E has non-split multiplicative reduction at some odd prime Q. Of course, it will obviously have to divide the conductor. I will comment later on how important some of these hypotheses are. Second hypothesis is going to be that E has good ordinary reduction at P, and maybe I should say also P at least 5. Again, that's not that important. The third condition is going to be that the p torsion Galois module is an irreducible Gal Q bar over Q module and ramified at Q. So we see residually at P the ramification at Q. This is just a technical issue. Can be made to go away. D, finally, we'll get into these two conditions. So then with that in hand, if this has co-rank 1 and E, that the restriction map at P is surjective, then the rank of E, the Mordell-Weil group, is 1, and the derivative is non-zero. So that's going to be the conclusion of the theorem.
And L vanishes.
Actually, so this co-rank being 1, yeah. And if you want L of V1 is 0, put that in there too if you like. It's sort of supplied by that. So, as I'll comment later, you can actually replace these two statements about the p-infinity Selmer group with statements about the p-Selmer group, just the Selmer group at the prime mod p on the p torsion. And so that's something that one could actually, imagine computing. Maybe I should just say that now. I don't really like to use that board. We'll leave that up there. So maybe the first remark. So I guess maybe I should say that D and E are implied by the following. I'll call them D prime and E prime. So D prime would just mean, we'll just take the cell, the mod P Selmer group of E is just, say if it's Z mod P Z, if it's one-dimensional. And if the image of the restriction map here to EQP modulo P QP, so if that image does not lie in the image of, say, the P torsion in here, modulo P, EQP, P. So the image of that map. So if you assume these two conditions, then they apply these two conditions. So then, going back, I guess I've erased part of it, to this idea of proving a converse to the Gross-Zaqier kind of theorem, we can conclude theorem B, let E over Q be a semi-stable elliptic curve with non-split lit multiplicative reduction at some odd prime. Odd prime. Then we can say that, and I guess people want me to put this one in there too. But that's if and only if the rank is 1 and say Shavi is finite. So that would be the converse to Gross-Zaqier. Well, so I'm not making any hypotheses on the prime in the statement here, right? There's no p in the statement. I'm free to choose p to apply theorem A. So I'm just going to, so that I have lots of ordinary primes to choose from, and for most of them, these conditions will hold. And so then, so what's not obvious? So certainly it's going to be good ordinary reduction. It's going to be at least 5. Those will be obvious. That's obvious. So this is the only, let's check this. This is certainly going to be irreducible for all but a finite set of primes for elliptic curve, say using Sayre or something. And the existence of whether or not it's ramified at this prime q is a condition on the power of q that divides the discriminant of the curve in comparison to p. So again, I can choose a p such that everything is satisfied. This condition, Selmer of p of e having co-rank 1, is equivalent to this plus this. Or at least the combination of these two having co-rank 1. And the surjectivity here is equivalent to the finiteness of Shaw in that case. But somewhere, so you get this theorem from this. But this theorem, nowhere did we assume that we had any points, so we're going to have to produce a point somewhere. All right, so that's the converse to Gross-Zaqier that I was going to talk about. Maybe it's worth now commenting on some of these hypotheses. I'd say that the hypotheses on N and Q can be weakened. This is work in progress. They intervene only in some technical situations which will become a little more easy to explain as I sketch the argument. And if can allow, for example, additive or non-multiplicative reduction at a single prime, so at least one prime, say maybe 2, for instance, then you can also conclude following theorem, which Andrew and I are writing up. The elliptic curves, there's maybe I should just say it this way. A positive proportion of elliptic curves when ordered by height have algebraic, and that means rank, and that means the rank of the Mordell-Weil group, and analytic rank 1. And so that's the order of vanishing. at s equals 1 of the L function.
What does it mean if can? I mean if your theorem were true under the
Yeah.
hypotheses?
So if we can do this, what I can say, what I'm trying to do is say that I'm being very careful at the moment and saying what I have written down and so far is this theorem, but in the process of removing the hypotheses on E, and E at which point this would in fact be true.
Both to weaken those hypotheses and to allow at least one additive, and to allow exactly one additive reduction.
At least. If you allow, what do I want? Yeah, I guess I'm not being precise there. So if, for example, one could prove this same theorem here, for instance, when E has additive reduction at 2.
At P?
No, at 2. Not P.
At 2. Okay.
At 2.
At 2.
Then you would have this.
So everything else is the same except it has additive reduction at 2.
That's right. Then that's all you would have to do. Is allow in the proof of this the elliptic curve to have additive reduction at 2.
But otherwise.
Otherwise, all the hypotheses can stay the same. And in fact, I mean, that's going to happen. So. I still don't want to use this board, but I also don't want to erase that theorem. I guess we have to do it this way.
But so in this conclusion,
Yes.
given what we know,
Yes.
it would be the same. No. To say that in positive proportion have analytic rank 1, since that implies we know that rank 1.
Yeah. You can take your pick. But that's actually not known. Even under, as far as I know, that's not even known under GRE. So somewhere in the proof of theorem A, we have to prove that there's a point on the curve. And the only way we know how to produce points on elliptic curves is through the Higner point. So it shouldn't come as any surprise. What I'm going to do is somehow under these hypotheses actually prove that the Higner point isn't 0. So let me try to motivate what's going to happen. So if we recall the Gross-Zaqier formula. So you have an auxiliary imaginary quadratic field intervenes. So we have K over Q, some imaginary quadratic formula, or quadratic field, sorry. And the usual Higner hypothesis is that the prime divisors of K, of the conductor split in K. And maybe I'm now going to assume, in addition, that the root number W of E is -1. Then, and so this has some discriminant D. Then the L function of the elliptic curve over S factors as the L function of the elliptic curve and the L function of its D quadratic twist. So this is the D quadratic twist of E. The Higner condition, together with the assumption that the root number of E is -1, tells me that the root number of E of D is +1. And so, in fact, then what we have is that the L prime of E over K at 1 is L prime of E at 1 times L of ED at 1. And what the Gross-Zaqier formula, or one variant of the Gross-Zaqier formula, says is that if this value wasn't 0, and since I'm free to choose k, I can always make that happen, then in fact we have that L prime of E over k, 1, is up to some constant the canonical Néron-Tate height of a point. And so P of k is some Heegner point. Associated to k. And this involves a modular parameterization of the elliptic curve that's tending the cusp at infinity to 0, and then P of k is the sum of Galois conjugates of a particular point here over the Hilbert class field of k. And so we can choose, we're free to choose our imaginary quadratic field with a lot of flexibility. We can always choose this to happen. So if our L function, in fact, if this L function only vanished to order 1, so if this derivative is not 0, and this is not 0, then in fact our Heegner point is not 0. So we have a point. So conversely, if we knew that the Heegner point wasn't 0 and we had chosen k such that this L function didn't vanish, then this would be telling me that the derivative doesn't vanish. And so this is the expectation of Bergson and Dyer when we start off with the elliptic curve that has rank 1 is of course compatible with sort of proving that the Heegner point is non-torsion precisely in this case. So I'm going to talk about a way to prove that the Heegner point is non-torsion, but I'm not going to prove that its height isn't 0, at least not directly. Instead, I'm going to just prove that the point isn't torsion. And so we want to prove, we want to prove that one of these Heegner points has infinite order. In fact, under the hypothesis that the Selmer group of E has co-rank 1, this is enough. This is enough for all that we need. Choosing k such that this is true means that the Mordell-Weil group of the d quadratic twist of E is finite. And so if there are any infinite points on the quadratic twist, they have come from the points on the curve that we started out with. So we'll have produced some point on the curve, or at least shown that it's there if we prove that the Heegner point isn't 0. And because the hypothesis that the co-rank is 1 on the Selmer group, that means that the rank of the Mordell-Weil group was at most 1. And so it's equal to 1. And then by the Gross-Zaqier formula, we get the non-vanishing. So instead, so we do this by showing that the formal log of pk is non-zero. And the formal log is for some prime of some finite prime of k. Some finite k. So we're going to assume that p splits in k. Okay, and we have the maybe I should put kb there. The formal log, which comes from maybe up to scalar, it's determined. So we choose a 1 form. So omega a 1 form on E over Q. And we could normalize it. So so if we pull this back under our modular parameterization, this is going to be some non-zero constant times a new form. And we can choose to normalize that constant however we want. That's just going to change this by a scalar. And so what we want to prove is that this is not 0. And that would imply that P of k is non-torsion. Torsion points being in the log. Of course, you can just think of this as some sort of Lie or some analytic group over kV, and this is just the log, usual log. But most people who see elliptic curves first through Silverman's book probably first see it as the formal log. So we're gonna prove that that's not 0. So, and to do this, we use a formula of Bertolini, Darmon, and Prasanna, which expresses the formal log, or its square, up to a non-zero constant, as the value of a p-adic L function. So in fact, there exists work of Bertolini, Darmon, and Prasanna. Actually, this goes back to Rubin in the case of complex multiplication. There exists a p-adic L function that's associated to a choice of one of those primes above P and K. This is where I'm using the hypothesis that P splits in K. And so the elliptic curve. So it's really a function of the elliptic curve over K. And the variable is going to be a class of Hecke characters, of anticyclotomic Hecke characters of K. I'm not going to sort of define this really appropriately. What I'm going to tell you is what it interpolates. This interpolates the usual values of the L function of the elliptic curve over K, twisted by chi over suitable CM period. And so this is the L function evaluated at 1 for chi, an anticyclotomic Hecke character of K, unramified at all finite primes, and with the infinity type, and such that this infinity type is given by z to the n, z bar to the minus n. That's the anticyclotomic thing. So n is going to be congruent to 0, mod p minus 1, and positive. So these are then Hecke characters whose weights are larger than the weight of the modular form. So this is the Rankin-Selberg L function of the modular form for our elliptic curve, and a CM modular form of weight n plus 1. And then we're looking at the central value of that. The sign of the functional equation in that family is actually plus 1. It's the opposite to the sign in the usual Gross-Zaqier family, because we're now allowing the weight of our character to be larger than the weight of the modular form, or the elliptic curve, which is 2. But we're going to specialize it. Yes? The period of E doesn't come in because this has the dominant weight. So it's a suitable CM power to CM form to something that depends on n. So but the period of E does not intervene. You can think of that as, if you look at the usual sort of Rankin-Selberg method, you would take your modular form for your elliptic curve, multiply it by an Eisenstein series, and hit it with the Hecke projector for the CM form. So only the periods for the CM form would show up. That's one way. Otherwise, I mean, you can also think of it in terms of Deline's period. So what Bertolini, Darmon, and Prasanna prove is a identity that expresses the value of this p-adic L function at a point outside of this set of interpolation in terms of the log of the Heegner point. So what we're going to do is I'm just going to write down the Etp formula, which is that the value at the trivial character, so that's certainly not satisfying these conditions, and it's 0, and so it's not positive, that this is up to some constant, which I'll just write as star, that this is the formal log of the Heegner point squared. So why might you even imagine such a formula? Well, it comes through the Walsperger formulas expressing this L value as a square of some torus period. So basically what's happening is you have a formula of Walsperger that's telling you that the L function of E twisted by chi, one of these sort of algebraic chi's, evaluated at 1, is the square of some torus period for, we have the modular form now phi, which is going to be the modular form associated to the elliptic curve, t, and then we would have our characters chi, t cross t. But actually what you have to do is you have to apply sort of the Ramanujan theta function, or differential operator to raise the weight of phi of e some number of times. So since it raises the weight by 2, I'm going up incongruent to 0. So it's n minus 1 over 2 times, I think. So it's some number there. And then as n goes off to infinity, or actually as the power of p that divides n goes off to infinity, I can choose this to go down to minus 1. I can do, so maybe it's n.
n minus 1.
You're right, because this is actually weight 2n. Yeah. Right, it's n minus 1. So I let n go off to 0 p-adically, and I'm going to get I'm going to get this, because this is equal to this, as I let n go off to 0 p-adically, I'm going to get to this value. And then what I want to do is sort of identify this as this side. And this is Coleman integration. Basically, this log function can be thought as the Coleman integral of this one form. Well, we're evaluated at sort of we would do the Coleman integral between the origin and pk of the one form. And so what do we want to do? So we want to find some primitive for omega. And that's what, p-adically at least, we want to find something such that when we apply the Ramanujan operator to it, we get omega. And so p-adically what we want is delta minus 1, delta to the minus 1 of phi. And we can find this p-adically here. So that's the spirit of the Bertolini-Darmon-Prasanna formula. And so once we have this formula in hand, though, the idea is to now to try to use it. So we want to connect now the non-vanishing of this L value outside, an L value of a p-adic L function outside of the range of interpolation to something that we can have seen by our hypotheses. So the next step So the next step show that this L function E over k1 is not 0. Then the log of our Heegner point's not 0, and Heegner point's of infinite order. And so we do this through Yusawa theory. So there's a large body of conjectures that relate p-adic L functions of this sort to the characteristic ideals of p-adic Selmer groups. So there's these Iwasawa-Greenberg main conjecture. Identify this p-adic L function as the characteristic ideal of a certain p-adic Selmer group. Instead of going off into defining this Selmer group, I'm going to say one consequence of this would be the following. Is that, so if we had this sort of identification, that then we can say that if this value vanishes, then a certain cohomology group is not 0. So what is this? So V here is the p-adic Tate module of the elliptic curve, characteristic Tate module. And this means so classes are unramified at all places of K that don't divide P, and split at the conjugate place, V bar, with no conditions at V. So this is not the usual Selmer group for the elliptic curve. This is the Selmer group that would be associated really to these sorts of L functions if I had included one of those Hecke characters in there. What's that?
What does split mean?
Split, 0. And 0 at V. So it's then an exercise in Galois homology to observe the following, that our conditions D and E on the Selmer groups in theorem A can also be expressed as saying that if we look at the usual Bloch-Kato Selmer group for Q, for V, that the restriction map is just an isomorphism onto the local Selmer group. So the F here is the Bloch-Kato condition. So these are the usual Selmer groups. And our choice of K, in fact, that tells us then that HFK, actually it tells us the following, that H1F of Q of V maps by restriction to H1F of K of V, and that's in fact an isomorphism. But that's because since H1F of Q of V, insert the character associated to our imaginary quadratic field, chi of D, is the Selmer group of E of D. And we've assumed that the L function doesn't vanish, so that this is equal to 0. Since the L function of E of D of 1 is not 0. I don't actually have to invoke Gross-Zaqier to know this, because I'm working at a prime of good reduction. I can actually refer to Kato if you want to just bring in something else. Or Kolyvagin. And that this observation is actually enough to imply that h1v of k of v is 0. This is some argument with Galois homology and duality. It's very much in the spirit of Euler systems, actually. And so we have that this is 0. And so, so in fact, if we can prove this implication here, which is just coming out of Iwasawa theory, then we would know that this had to be non-zero under our hypothesis D and E. And we go backwards, and we see that the Heegner point is of infinite order. So this implication is actually the key. This is the key. And this is precisely the kind of implication that I have been working on in some form or another, or some variation or another, for the last few years with Eric Urban and with my students. And in fact, Shin-Wan has worked out enough of this, one half of this main conjecture to deduce this implication. And this is so under the hypotheses of the theorem, Shin-Wan has proved this. And so that's the argument. Let me say maybe a few words about then how this is proved, and maybe a little bit more about the hypotheses then and how they intervene. Let me also say that in the end, we don't manage to work in the classical Gross-Zaqier setting. We actually have to allow our imaginary quadratic field to be ramified at a prime where the elliptic curve has bad reduction. And so the final statement that sort of says, now that you have this Heegner point being non-zero, you want to conclude that the L function is not zero. You can't really refer to the formula of Gross and Zaqier. You have to refer to this more general formula of Wan, Zhang, and Zhang. So it's all sort of mixed into the pot and stirred around. Why is that happening? That also has to do with how this implication is proved. So the idea is we have our modular form. So we had our elliptic curve. And so then there's some associated modular form, right, to new form. And then we choose our imaginary quadratic field K. And we want to move this to a definite unitary group. And so to do this, we're already having to assume some kind of ramification hypotheses on F. Because if we're going to do this over Q, then there's going to have to be some finite place where F is square integrable and the like. And then, so we get some automorphic representation here, and then we'll have our Hecke characters. Well, actually, we also have to choose an auxiliary Hecke character to make this change, and the weight of that Hecke character needs to be larger than the weight of the form, and so that's you can see things like that. So there'll be. So this is pi. So you get something associated to a pair here. Let's call that sigma. And then one forms an Eisenstein series on U31. So you get some Eisenstein series associated to sigma. And the constant term, so this is coming from the parabolic that stabilizes an isotropic line, is going to have Levy, which is U2 cross GL1 of K. And so you can actually add in an auxiliary another Hecke character we'll call tau. So you get some Eisenstein series. And the constant terms of this Eisenstein series involve these L functions, or these L values. Involve the L values. L of F chi1 that we talked about before. And chi is related to psi and tau in a way which I'm not making terribly explicit because it doesn't really matter. And then one wants to show then that if the L value we're interested in was actually one of these sort of classical L values, then we might say, well, we want to know if this is 0 or 0 mod p, that our Eisenstein series is sort of looks like a cusp form. And so this can be done, you do this p-adically. This p-adically, and you show that sort of the E sigma as tau is varying p-adically is congruent to a cuspidal family at chi being the additive, or the identity character. And then you use the Galois representation attached to such cuspidal families to construct sort of elements in the Selmer group. And so then a lot of it boils down to trying to prove this congruence here. And you can compute the constant terms of the Eisenstein series fairly easily. And then what you want to know is that if something divides this constant term, then it doesn't divide some non-constant term of the Eisenstein series, so that you actually have a congruence that isn't just saying that something is 0. And that requires a computation of the Fourier-Jacobi expansion, or at least some coefficients of the Fourier-Jacobi expansion of this Eisenstein series, which is fairly involved. And it turns out some natural linear combinations of them are expressed as products of these sorts of L values with L values with Hecke characters that are of finite order. And then you would want to know that each factor, say, in that product doesn't vanish. And the only thing that saves you is that you're actually here. Of course, these characters are varying in a particular family. But when you take these linear combinations of the Fourier-Jacobi coefficients, you get to choose, in some sense, the family of Hecke characters that you're working with. And we have enough non-vanishing results from much of the work that's been done on equidistribution of Heegner points and things like this to conclude that some Fourier-Jacobi coefficient doesn't vanish at this chi equals 1. And then you get the congruence that's needed. And so the conditions that I wrote down of n being square free, the conductor being square free, only intervene in the computation of these Fourier-Jacobi coefficients. And it's mostly a matter of laziness, in fact. And so with some computations in progress are to remove those calculations. And so maybe I should just sketch to remind you what was the path of reasoning here when something like the following. So we start off with our assumptions on the Selmer group from Theorem A. So this tells us, so the first step was, if you reverse this backwards, this is just telling me that this is isomorphically. So what I'm really assuming is the non-vanishing of the sort of Galois regulator. And yes, thank you. So that's QP. So this is the restriction. so those assumptions are equivalent to this at the prime p. And then we choose k such that, in fact, what we have is that h1 q of v is isomorphic to h1 f of k of v by restriction. That's the global one. So there's no. So we just choose that k, and then we get that. And actually, the more important conclusion is that h1 sub v of k of v was actually 0. So far that's just Galois homology. And then we feed in this implication primarily due to Shin 1, then that the log of, well, actually I should say this, that the p-adic L function isn't vanishing at that point. And then by the theorem of Bertolini-Darmon and Prasanna dp, then we have that the Heegner point is non-torsion. Okay. And then this implies that, in fact, E of Q has rank 1, and the L prime of E of 1 is not 0, and I'm supposed to put L of E of 1 is equal to 0. Okay. Yeah. As well. And here, this is like the Gross-Zaqier-Kolyvagin slash Wang-Zhang-Zhang, and if you don't want to use Kolyvagin, you can build a Kato at one step. So that's the spirit of the proof of Theorem A. As I said, then it becomes another sort of simple exercise in Galois homology to just check that D and E are in fact implied by these relatively simple hypotheses on the P-Selmer group, which was just that was Z mod PZ, and the image of cell P of E in EQ with P mod P of EQP is not contained in the image of the P torsion points over the local field. So this is the kind of thing that for small primes like P2 equals 2, 3, 5, say, that Bhargava and Shankar can try to count, actually. And so this kind of condition is very much the sort of condition that they've counted before. And so then it's not unreasonable to go and ask them, can you just say something about this? And they have a very nice theorem now that proves sort of equidistribution of the non-zero points of Selmer P in these in families where you can think of this group as being constant. So if they're p-adically, all the elliptic curves are p-adically close enough, then that's a constant object. And then you can prove an equidistribution result on the image of Selmer as the elliptic curve runs over those elements in the family, so you can get a sort of positive proportion of curves satisfying these two conditions. So I should stop there. What do you mean by chance? I don't see a way to get higher rank in terms of points in any reasonable way. Yeah. So it's the obvious question.
What is the proportion, do you know?
What is the proportion? It's positive. It's small. Larger than 0, though. No, I don't know it off the top of my head. Zero. What? Yeah. 1%. Let's say 1%. It's provable. You get better and better percentages by improving the hypotheses on the theorem.
So P and a 3 and a 2.
What you can say, even under the hypotheses of theorem A, is that a very sizable percentage of elliptic curves have either algebraic and analytic rank 0 or algebraic and analytic rank 1, but you don't necessarily know the percentages of either set. But together, rank 0 and rank 1 make up a pretty sizable percentage of the set of curves.
Sizable?
I would say already probably about 25%. Would you? Yeah. It should be 100%. So at least 25%. Sorry, show you were.
I mean, from P2 and 3, you like P bigger than 5.
So P bigger than or equal to 5 for theorem A is again laziness. It's certainly true at P equals 3, and when all the writing is done, it'll be included. For 3 at the moment, actually, our first stab at combinatorics for positive proportion, actually you need P equals at least 5. It doesn't tell you anything at P equals 3. Maybe if you combine 3 and 5, one could say something. I should say that when you order the curves by height, like it's done, most curves are supersingular at 3. So you actually have to go and deal with the supersingular case, and that's another thing that we're dealing with. The ordinarity isn't really, for elliptic curve, isn't so important here because most of the ordinarity comes from choosing P to split in the imaginary quadratic field because we're working on these other unitary groups. For P equals 2, I've always been afraid of 2, so I just haven't thought about it. And so someone else was starting a question. And then